I'm getting myself situated here. We'll get started in a second. Those are the grades. Exam 1, we had average was 66, and exam 2 it went up to 79. And here's the grade. Here are the grades. Okay, so welcome back. Hope everyone had a good weekend. The grades were good. You know, I think part of that was the, well, that y'all were ready. That's a good thing. But then also that, you know, they had that built-in 20 extra points you could get. So I think that that really helped a lot of students, which was the intention, all right? Was to kind of build something into it that would allow you to do well. So in the work, for the most part, what students turned in was good. So as you can see here, we have, you know, we had no C's and no D's, which is really odd. We just had A's, B's, and then some failing grades, and that's it. So we have an upside down bell curve. Everything is backwards. It looks like, oh, where's my little thing? Well, I got to open something up. Give me a moment. Where did that thing go? There it is. So we have what's called, geez, upside down bell curve. So normally we like to see curves that go like that, where you have a lot of people, the average is somewhere in the middle. You got a few people that do really well, a few people that struggle, but everyone's kind of grouped together. We have an upside down bell curve, which is very, very common in math classes. All right, any questions or comments about the exam? We're good? You ready to move on?
Actually, I was wondering if you can go over a problem, but I'm trying to find the problem real quick. I think it was number 8, I want to say, on the exam. Or would you not have time to do that?
I can look at it. Let me look at it first. Give me a moment. I got to do this off screen here. Looking for the key. I don't remember where I put the key. Where the heck did I put it? Oh, you know what? I know where it is. It's my other class. No, it's not. Where the hell is it? If I can't find it in the next 30 seconds, I'm not doing it. Where in the world is it? It's today, the 19th.
Today's 19th, yeah.
Okay. All right, well, I'm gonna have to bring up the exam. I'll just have to look at the problem. So let me open up the exam. I don't know where my solutions are. They're around here somewhere. I can't even find the exam. Where the hell is it? What the hell? Okay, I don't even know where the exam is, to tell you the truth. All right, I have to go back to the old school. Here it is. Okay, so what about number 8?
I was confused about the I guess the way that I did it, I ended up getting, I used the integration by parts method on it,
Yeah.
and I ended up getting x times the natural log of sine x for the first part, and I'm pretty sure that was wrong. So I was just wondering, like, what I probably should have got for that first part.
Okay, so let's just look at the integral, not the limits of integration, just the indefinite integral. So your integration by parts, right, should have been this. Arctan here and x here. And then the derivative of arctan x is 1 over 1 plus x squared, and then the antiderivative of x is 1/2 x squared. Is that what you did or no?
Yeah.
Okay. So then ultraviolet would be 1/2 x squared arctan x. And then minus the integral of voodoo, which would have been these two multiplied.
Oh, I see where I went wrong now.
And I can bring the half out, and then I would have had x squared over 1 plus x squared dx. And then on this, you do partial fractions. So you do long division first. And then after long division, it's pretty straightforward. Okay. You could also be real clever and just do an add 1 minus 1 on top. If you do an add 1 minus 1 on top right now, you can split it. You can put all that over the denominator, which is 1, plus then you do the negative 1 over that. So you get another integral that has negative 1 over this. And then each of those is just straightforward. That just, all that does is skips the long division step.
Okay. I understand.
Make sense?
Yeah, that does.
Okay.
Appreciate it.
Yep. Okay, let's get to today's material. So what we're going to do now, we're a little behind, okay? We're going to try and cover 6.6, which is called Improper Integrals. And the idea here is that we already know how to find the area. Well, let me say this. 6.6 is broken up into two sections. There are two ideas here. We have what are called type 1 improper integrals. Type 1, those are called infinite intervals. Then we have type 2, which is going to come later. All right, I'm not going to talk about type 2 yet. That'll be next class. So the key thing here is that these are called improper integrals. And what makes them improper is that they're not as straightforward as what we've been doing. So far, we've been doing these definite integrals where we have this notation now. And all this means is we have some function f, and we're going to start it at some point A, and we're going to end it at some point B, and we're going to calculate that, and it's going to give us the area underneath the curve, right? That would be, I guess, if you want to call it something, a proper definite integral. What makes an improper integral improper is that there's something different about it. We've got trouble, all right? We've got trouble with the integral. And the first type of trouble we have is when we have what are called infinite intervals. So imagine that we wanted to take this picture I have here on the left, but instead of actually stopping at B, I don't want you to stop. I want you to just keep going forever. Just whatever the function does forever to the right, I want to know, can we talk about an area? So maybe our graph looks like this. We got some function here, and it keeps going to the right. We still started at A, but we never end it. So we just let this go to infinity. Then we want to try and see if we can't find that area. Now, intuitively, you may think, okay, well, look, the area has to be infinite then, because we're going to go forever, right? Does that seem intuitive? And, you know, for a lot of functions, that would be the case, because you're going to continue to have area, you know, no matter what happens as you go out to the right. But what if you have a function that does something like this, where you start at A, but what if the function like does some stuff, but then eventually starts to asymptotically approach 0? So the graph starts to get closer and closer and closer to 0, never actually getting there, but getting smaller and smaller and smaller. So then if you have something like that, you know, you're talking about that area down there. Do you all agree that that area, the contribution as you keep going to the right, the area is getting smaller, but it's still there, right? So you might still be thinking, oh, it still has to be infinite. It's going to turn out that that's not the case. Sometimes you do get infinite area and sometimes you do not. Sometimes you actually get a finite number, which is really strange, but that's the way it works. So we have this new notation, right? This new notation here on the right. We either have an integral that starts at a and ends at infinity, which is the picture that I just drew right here, or we could go from negative infinity to b. Now, let me show you what that would look like. That would be something where we have our function stops at b. Oh, that's a b. And we're looking for the area over here this way to negative infinity. So we're trying to figure out that area this way. That would be the second type, or the second type of interval we have. Or we could have an interval where you go from negative infinity to infinity, which would be in both directions forever. Okay, and that would be this case where we have a picture that looks like this. Here we've got some graph. We want to go that way forever and that way forever. And we want to see if we can figure out the area in the middle there. But you go forever in both directions. Does that make sense? I mean, what we're going to try and do? And does it make sense to you why we call these infinite intervals? Do y'all see that every one of these intervals, whether it be a to infinity or negative infinity to b or negative infinity to infinity, if you were to look at those intervals on the number line, they're infinite, all right? And that's what makes it a type 1 improper integral. So the question remains, how do we do these, right? How do we do these? Well, the idea is actually pretty simple. What we're going to do is we're going to say, all right, let's say we want to do this. Okay, let's say we want to do this. So we're going to be looking at a function. We're going to be starting at a. We're going to be going to the right. What we're going to do is we want to go forever. So what we're going to do is we're going to fix this value and we're going to call it t. All right. So right now, this would give me an area, wouldn't it? Like if I just went in here and I asked you what's the area, that it would give you one. But what we're going to do now is we're going to take a limit and we're going to let t go to infinity. So what that's going to do is it's going to take this right endpoint, it's going to drag it out forever. All right, and that's why you'll see here on this notation, here's the definition right here. Let me zoom in on that so you can see it. This is the definition that we're going to be using right here. That is how we calculate an infinite interval. We are trying to go from a to infinity. So what we do is we replace the infinity with t, and we put a limit out front. We let t go to infinity, and then we just do this integral the way we've been doing them. All right, so let's do an example. You'll see this all kind of play out. Let's do our first example. Any questions? Okay, the first example that I'm going to do is, let's do the integral from, let's see, let's go from 1 to infinity of 1 over x squared. Right, so we first need to know what 1 over x squared looks like. Well, I mean, we don't need to, but it would be helpful if we knew what 1 over x squared looked like. So I could go and pull up my graphing software, but I'll just slap it in here for you. This is what 1 over x squared looks like. And I think all of you would agree that if I start at 1 and I try and find this area over here to the right, that the area is getting smaller and smaller and smaller, but I'm going to go forever, right? So the question is, do we get a number here? Like, do we actually get an answer? Or does that area become infinite? So let's see what the actual calculation gives us. So what I'm going to do is I'm going to replace the infinity with t, and I'm going to let t go to infinity. So I leave the a to be 1, and then the infinity becomes t, and then I'm gonna do 1 over x squared dx. So really just kind of focus all of your attention right now on this in orange. That is a definite integral now, right? Like 1 is a number and t is a number. We don't know what it is right now, but we can do the fundamental theorem of calculus on this. All right, so we're gonna just keep the limit out front. We're going to do what we did before, which is find the antiderivative of this. So I'm trusting that everyone here could find the antiderivative of 1 over x squared, right? That's just power rule. That's just x to the -2. So the antiderivative of that would be -1 over x. I'll let you confirm that on your own. And then we have the evaluation bar, and we're going to go 1 to t. Now we do what we did before. We're going to leave this limit out here. And now I'm going to put in 2 spaces here for me to evaluate. So the first thing I plug in is t. So I'm going to replace x with t. So I just get -1 over t. And then I'm going to plug in 1, which gives me -1 over 1. Now, the right side of this minus -1 is going to just become +1. But we still need to figure out now what's happening to this piece, -1 over t, as t goes to infinity. So right now I need to kind of be thinking about, you know, this is what I'm looking at, the limit as t goes to infinity of -1 over t. Okay, so this is kind of like scratch work I'm doing on the side. Now, where does that go? What's that limit?
0.
0, right? That goes to 0. Okay, because your numerator is -1, the denominator is blowing up, it's getting big. Anytime you have a number that's fixed on top and a number on the bottom gets huge, that fraction goes to 0. So we know that this is headed to 0 in the limit. Notice I didn't write limit anymore, right? I just put that this is equal to, because I already took the limit, and that's just equal to 1. All right? So what this is saying to us is that if you were to look at the area underneath this curve from 1 to infinity, that the area is 1, which is a finite number, right? This is a finite number. So since this is finite, we will say that this integral right here, we will say that it converges to 1. Okay, that's new terminology. We've heard converges before in Cal 1, but now we're talking about the convergence of an integral. An integral is said to converge if, when you do this limit, you get a number. If you get a finite number, then we will say the integral converges. All right? Okay, now I'm going to try and illustrate this with something real quick. I'm going to bring up this Desmos. Desmos is really awesome. 1 over x squared. Okay, so there's the graph, right? Now watch this. I can put integrate. Okay, so it already put an integral symbol in here. I'm going to say 1 to t, and I'm going to do 1 over x squared dx. Oops. Dx, and it's going to ask me, do I want to control the t? Like, do I want to make t a slider? So I can control the value of t. Let me double click on this. I want t to go from 1 to, let's say, 1,000, and it'll increase by 1 each time. Okay, so watch. Right now, t is 1. So we're going the integral from 1 to 1. And we learned last time with properties of integrals, if you ever go from a to a, same number, the integral gives you a value of 0, which is why I have a 0 here. So now if I move this to the right, let's say I make it 6. If t is 6, we're doing the area from 1 to 6, and you can see it's calculating it to be 0.833. no matter how far I go, I'm going to be a little bit smaller than 1, no matter how far I go. So now I'm at 46. You see the values 0.97826. As I keep going here, 0.99465. Well, I'm still at 0.99998. So, okay, when I go out to 1,000, I'm at 0.999. Let me go further. Let me go to 10,000. Let me see, how far do I have to go? I have to go out to almost 10,000 to get 0.999. So what's happening is the further you go, do you see it's getting closer and closer to 1? If you ever stop, you're going to be a little bit short of 1. But if you could go forever, it would be 1, which is a weird idea, right? That area is bounded. It will never exceed 1, ever, ever. Okay, let's try a different function. That was 1 over x squared. Let's try the same interval, 1 to infinity. How about just 1 over x? 1 over x instead of 1 over x squared. So I'm gonna come back to Desmos. I'm gonna change my graph to 1 over x. Okay, there's 1 over x. And you can see here that as I start at 1, so if I go from 1 to infinity, I'm doing that area in there, right? There's still area as I go to the right, so, but it's doing the same thing that 1 over x squared did. It's dying down, right? It's asymptotically approaching the x-axis. Do we get the same result? We're about to find out, right? Change this to 100, and I'll come back to this in a minute. So let's do the work. So the first thing we do is we replace the infinity with t and take the limit as t goes to infinity. We all know that the antiderivative of 1 over x is the natural log of x. Now, I should put the absolute value on the x, but I'm not going to. And the reason I'm not going to is because we're going from 1 to infinity, aren't we? And so the x value is always positive. The only reason you would ever need the absolute value around that x is if you were plugging in negative numbers. You would need to take the absolute value so it's defined. So because of the interval I'm looking at, I'm not going to put absolute value. Now we just evaluate at the 2 endpoints. T goes in first, and then 1 goes in. The first part of this is pretty straightforward. Natural log of 1 is 0. Hopefully you know that. If you don't know that, well, you can do it on your calculator. The other part is to figure out what's happening to this piece here. So I would need to know what is the limit as t goes to infinity of natural log of t. And can someone tell me what that limit is? Or can someone tell me how you would determine what that limit is? Natural log of t. You need to know what that function looks like. What does the natural log of t look like? So this goes back to college algebra. The natural log function looks like this. That's the natural log of x. So if we're saying what happens as the argument in here goes to infinity, what you're asking is, what does this function do as you start going to the right forever? So what does the natural log function do as you start going to the right forever? Where does it head? Heads up, right? Heads up to infinity. So as we go to the right, the function heads up to infinity. And that means that this thing heads to infinity. And infinity minus 0 is still infinity. And so what does that mean? Infinity is not a number, right? Infinity is like an idea. So we're not getting a finite number, right? This is not finite. It's actually infinite. In the case that we get this to happen, we will say that this integral diverges. And you don't say it diverges to infinity, just say it diverges.
Sir, I had a question I wanted to
Yep.
ask you.
On the what?
I had just a random scenario that I wanted to ask you.
Okay, go ahead.
So let's say we're doing an integral, and once we get to the evaluation part, we get infinity over infinity. What would we do in that situation?
L'Hopital's rule.
Oh, gotcha. Okay.
It's coming today. Yeah. Yeah, we're going to have that happen today. Good question. Okay, so let's go back to Desmos and let's see what happens here. If I change this right here to 1 over x, then notice right now we're going, oh shoot, we're already at 100. Okay, so if we go from 1 to 1, we have no area. If we go from 1 to, let's say, 14, we have an area of 2.6. But as I keep going out, look at that number, it's growing, right? Now it's 4. Okay, so does that mean it's getting closer and closer to 5? Well, maybe, let me see. Let me go out to 1,000. So is it getting closer to 5? Oh, no, it busted out over 5. Okay, so maybe it's getting closer to 6. Nope, it got past 6. So maybe, well, maybe it'll never get to 100. Well, it depends on how far out I go. So I'm out at 100,000 and I'm only at 11. Does that make sense? So do you think it'll ever get, do you think this number here will ever go past 100? What did our answer tell us?
I think at some point it'll go past
At
100.
some point it will. We just have to make this number big enough. And I don't know how big Desmos will let me go. What is that? 10 billion? So let's see if we can get past 100. Oh, what? Undefined. Okay, so I think that the computer's having a problem with this. Yeah, I think we're beyond the tolerance of what the computer can do. That's just a limitation of the computer, all right? So we'll go to Wolfram instead. All right, so we'll go to Wolfram and let's integrate 1 over x from 1 to, let's go out to, you want to go out to 10 billion? What was it? Was it 10 billion? $23. So let's go out even further. Maybe we can go 10 to the 10th power. No, let's go to the 20th power. I don't know how much this will be able to do. Okay, so if we go to 10 to the 20th power, we're now at 46. Okay. If we go to 10 to the 30th power, at some point it's going to give up. 69, now we're at 69. Okay, so 10 to the, I really think we're going to find the limit of what Wolfram can do. These are big numbers. 138, there we go. We got past 100. Now, could you get past 200? Yes. Could you get past 1 billion? Yes. How far would you have to go out? Further than you can even comprehend, but how far can we go? Infinite, right? So this area, even though it's getting smaller and contributing less and less each time, it is still becoming unbounded, that area. Does that make sense? Let me change this to, let me change this 10 to the 10th power. Let's go back to 1 over x squared, because we said that one converged, right? And we said it never got bigger than 1. So let's see, if we do that, it's gonna be like 0.9999 something probably. Ooh, it's having a harder time than with this one. Oh, because I'm squaring it. Approximately 1, okay. It's 9,999,999,999 over 10 billion. which is basically like 0.999999999. Like, what is that, 7 or 8 nines? Okay, do you get the idea? One of the examples I gave you converged to 1. The area is finite. The second example I gave you, we did not have convergence. We had divergence. So in the notes, what we say here is that if these limits exist, so if we actually take this limit, if the limit exists, that means we get a finite number, then we will say the integral is convergent. If the limit does not exist, in other words, it's infinite or does not exist, then we will say the integral is divergent. Okay, so let's do another one. How about this? You tell me what you think is going to happen here. Just tell me what you think. Convergent or divergent? I don't want you to work it out. I just want you to think about it. What do you think is going to happen?
Convergent.
Convergent? Why? Why do you think that?
I think it's going to be bigger.
Because the power is, you're not going to get a natural log out of it, basically, when you take the antiderivative.
This one converged, right? 1 over x squared converged. And the reason it converged is because this right here is getting smaller, right? But it's getting smaller really fast because the bottom is x squared. Where when we had this, even though this 1 over x is going to 0, it's not going to 0 as fast as 1 over x squared is. So it seems reasonable that this one right here, that gets smaller even faster than 1 over x squared. So that should converge. I'm going to leave it as a question mark. It should converge. And then Alex also said that this one right here, the antiderivative is natural log, but both of these two are going to be power functions. So those should go to 0 when we take the limit. How about this one? What do you think this one's going to do? Think about how fast this thing is going to 0.
I think
Maybe
it'll converge.
You think that will converge?
Yeah, because I'm thinking about it like if it's x to the half power.
Mm-hmm.
That's how I'm thinking about it in my head, at least. And then it would be a power function when you take the antiderivative of it.
That is correct. That is correct. It would be a power function, but is that the thing that's really controlling things here? Look at these two, compare these two. Which of those two goes to 0 faster? So which denominators are bigger there? X or square root of x? Which of those two is bigger?
Wouldn't x be bigger?
X is bigger, right? So even though this is going to 0, it's not going to 0 fast enough to get convergence. And this is also going to 0, but it's not even going to 0 as fast as that one is. So maybe that's not convergence. Maybe it's divergence. I don't know, right? We would have to check, wouldn't we? So let's just see if we can't do this in a more mathematical approach, which is, why don't we look at this? What if we have an integral that goes from 1 to infinity of 1 over x to some power p? And I'm not going to tell, we're not going to say what p is. All we're going to say right now is that p is a real number. It's fixed, okay? So p is a fixed number. Maybe we can just take this general statement and then make some conclusions on whether or not we get convergence or divergence depending on what p is. So just follow me through this. Let's see if this makes sense. I'm going to take the limit as t goes to infinity. I'm going to replace the infinity with t here. And I'm going to rewrite 1 over x to the p as x to the negative p. Like that. That's just me bringing it up as a negative exponent. Now I'm going to do fundamental theorem of calculus. So the antiderivative of that should be 1 over negative p plus 1 x to the negative p plus 1 evaluated from 1 to t there. Do you all understand what I just did there? That's power rule, right? That's our power rule on that function, but instead of having an n, we have negative p. So I just use that. The integral of x to the n is 1 over n plus 1, x to the n plus 1. We learned that very beginning of things. I just did that formula with negative p as the n. All right, let me come over here and break this up into 2 pieces. Let's plug t in for x. And then 1 in for x. What's 1 raised to any power?
1.
1. Okay, so that's all just going to become a 1 right here. So would you agree that this right side becomes minus 1 over negative p plus 1? Do y'all agree with that part? The thing we still have to figure out is what happens here. And this is actually a little tricky. We have to be extremely careful with this, all right? So right now, here's what I'm looking at. I want to know what is the limit as t goes to infinity of 1 over negative p plus 1 t to the negative p plus 1. And what's going to infinity here is t, right? The p is fixed. All right. So this is tricky. This is the tricky part. You probably have not seen something like this before. So let me just go back up for a second and ask you to consider something here. Right now, do we know whether or not that t is in the numerator or in the denominator? Do we know that? Because if you have t to a positive power, it's in the numerator, right? But if you have t to a negative power, it's in the denominator. So if that t was in the denominator, would you agree that you would have t blow up? Sorry about it. Sounded like a fighter jet just went over. If the power on t was negative, then you would have the t on the bottom, it would blow up and the top would be 1 and that thing would go to 0. But if the power on t is positive, it would stay on top, and if you let t go to infinity, the whole thing's going to blow up to infinity. Do you see the two differences there? So whether or not t is on the top or on the bottom is completely dependent upon this power right here, whatever that power is, right? So let's take a couple of cases here. If negative p plus 1 is bigger than 0, right? If the negative p plus 1 is bigger than 0, in other words, let me just move things around here. If p is less than 1, that's just me adding p to both sides here and getting 1 is greater than p, which is the same as saying that p is less than 1, right? So if p is less than 1, what can you tell me about this limit? What's it going to do?
Diverge.
Diverge. It's going to diverge because now you know that the power up here is a positive number, right? It's a positive number. Because we just said, what if this negative p plus 1 is bigger than 0? That means it's positive. That means the t is on top, and that means that thing's going to go to infinity, and this thing is just a number, right? Because p is fixed. So what you get is infinite. This thing diverges. Do y'all see that? This thing is either going to go to infinity, it's going to go to infinity, right? So that would mean we have divergence. Does that make sense? So that means that it would go to infinity, the whole thing would diverge. What do you think we should look at next? What if that negative p plus 1 is a negative number, right? If it's negative, then that means that p is greater than 1. So now imagine that this part in green is negative. That would drop it down, wouldn't it? It would drop it down and make it positive. So it would look like this. Limit t goes to infinity, 1 over negative p plus 1, but then we'd have 1 over t to a positive number. It was negative, but I dropped it down. That's why it's 1 over t. And now when you take that limit, where does that go? That thing goes to 0, right? And now we would have convergence, wouldn't we? We would have convergence. What's the one case I haven't looked at?
Equal
I know
to.
what happens if p is greater than 0. I know what happens if p is less than 0, but what if, sorry, not p. I know what happens when negative p plus 1 is bigger than 0. I know when negative p plus 1 is less than 0, but what about when it is 0? What if the power is, what if that power is 0? Wouldn't that mean that p would have to be 1? Just add p to both sides. And if p is 1, isn't that integral this? Isn't that the integral? That's the original problem. If I replace p with 1, come back up here to this. If p is 1, that's just 1 over x dx. And didn't we do that problem already? We just did that problem. This was divergent. So here's what we can conclude. If p is bigger than 1, or if p is 1, we're going to get divergence. If p is less than 1, we're going to get convergence. Wait, shit, I said that backwards. I apologize. Let me just back up because I just said that wrong. If p is 1, we get divergence. If p is less than 1, we got divergence. If p is greater than 1, we have the convergence, right? So let me try and summarize this. We know that the integral from 1 to infinity of 1 over x raised to any power should be equal to one of two things. It's either going to converge to, do we know what it's going to converge to? When it does converge, that's this case right here, right? That's this one. This part converges to 0, right? But come back up here. Remember, that's only this part, right? So if that thing goes to 0, then what's still left? This right here, right? This is the part that's still left. So in the case that we do have convergence, it's going to converge to negative 1 over negative p plus 1. And this will happen if p is bigger than 1. We will have divergence if the p happens to be less than or equal to 1. And so what we've just done here is we've come up with a general formula to handle 1 over x raised to any power. We can tell just by looking at the power whether or not we're going to have convergence or divergence. So back to the two questions I asked to start this off here. When we did this, I asked if that was going to converge or diverge. A lot of you said converge, but now we know it does, right? Because what's p for us here? It's 4, right? P is 4. And if p is 4, we're greater than 1. So that's going to converge to this. So this is going to converge to negative 1 over negative 4 plus 1 This is going to converge to, what's that, 1/3? And what about the other one? I asked about this one. 1 over the square root of x. And Peggy said that that meant that x to the 1/2, right? So p would be 1/2, and that would be this case. So we would just say it diverges. Any questions? Okay, let me ask this. Do you think that converges or diverges?
Converges
Why do you think it converges?
because p is greater than 1.
Okay, p is greater than 1, but look at my starting point. Starting at 1,000, right? So what we just determined, what we just did on the previous note is we said if we start at 1, right, and go forever, right, to infinity, we know that it will converge. So the area, this area right here, would be finite for this 1 over x squared, wouldn't it? If we started at 1, but we're not starting at 1. So this is finite. That area is finite because it converges. But we're not starting at 1. We're starting at 1,000. So that means we're only looking at this part. My question is that still finite? Does it make sense that it has to be? If the whole thing is finite, then if you start a little bit further down the road, you're still going to be finite. Now, we don't have the formula wouldn't work anymore in terms of we wouldn't be able to use this anymore. I couldn't tell you what it converged to, but what I could tell you is that it still converges. Make sense? Same with this. If I did, integral from 1,000 to infinity of 1 over x, that's still going to diverge because you know that starting at 1 and going forever, that the area in green is infinite, right? That's an infinite area. So if you start at 1,000 and only look at that, that still has to be infinite because this part from here to here is finite. So if this plus this adds up to be infinity and this right here is finite, then the whole thing has to be, or this one over here has to be infinite. This should not be labeled this way. This, let me get rid of that. We know that this, we know that this along the greens together is infinite, right? The greens together are infinite. But this section right here, just this section right here, has to be finite because we're starting and stopping from 1 to 1,000. That's got to be a finite number. So that would mean that this rest of this piece in here would have to be the part that's infinite. So starting at 1,000 doesn't matter. Doesn't really matter where you start. Okay. What about this one? Get you thinking here. How is that different?
Starts on the axis.
That one starts at 0, but what's wrong with 0?
It's undefined at 0.
Undefined at 0. You actually have a vertical asymptote at 0. Now I'm getting ahead of myself. That's what a type 2 is. A type 2 improper integral is where you have this discontinuity within your interval, but we'll get to that. That's next class. Okay, so let's not worry about that. All right, let's do another one. How about this one? This will be a fun one. This is the first time we've gone from negative infinity to infinity. I'm going to go graph this function for you. I'll give you a moment to write it down, but I'm going to go graph it. Okay, we're going to graph 1 over 1 plus x squared. So there it is. Okay. Almost looks like a little bell curve. Okay, it goes in both directions forever, gets smaller and smaller. So the question is that total area underneath that curve finite or infinite? Or sorry, I should say, is it finite or does it diverge? Okay, so let's do it. First thing is, how do we deal with this negative infinity to infinity, right? Does that seem reasonable? Like, what do we do with that? So here's the first thing I'm gonna do. I'm going to break this up into 2 integrals. The first one's gonna go from negative infinity to a number, and I get to pick the number, it doesn't matter where. I could pick the number 4, don't write this down. I could pick the number 4. And then I could say plus the integral that goes from 4 to infinity. So I'm using a property of integrals from last time, that if you wanted to do an integral from a to b, and you had some number in the middle c, you could go from a to c and then c to b. So you can break it up into 2 pieces. Now I chose 4, you could pick any number you want there, as long as it's between negative infinity and infinity. What's the most natural choice other than 4?
0.
0. So I'm going to go to 0, but you could use any number. I'm going to go 0 though. Now, each of these I have to do separately with their own limits. So I'm going to do this one first. And this is all going to be the next line. The part in red is going to become the limit. I'm going to let t go to negative infinity. We have not done this yet. Integral t to 0 of 1 over 1 plus x squared dx. Same principle as we just used, right? We're gonna, the part that's going to the infinity, whether it be plus or minus, we're gonna replace that with t, and then the limit's gonna contain where that t is headed. And then I'm gonna do this next part, which I'll do the blue one here. So plus this new limit. Now I don't wanna use t twice, okay, in 2 different limits. So I'm going to use a different dummy variable. I'm just going to use the variable s. Now, s, sometimes people confuse that with a 5. I'm going to use r. Feel free to use anything you want. R is going to go to infinity. I'm going to replace the infinity with r. And then 1 over 1 plus x squared dx. So you see that if you ever go from negative infinity to infinity, you're going to have to split it into 2. And each one of those is going to be its own limit. Yes? Okay, now we need antiderivatives. So do we all know the antiderivative of this? You better. Arctan, right? Arctan x. Evaluated t to 0 plus limit r goes to infinity, arctan x evaluated from 0 to r. And now I do these. Limit t goes to negative infinity, enough space for 2 things, plus limit r goes to infinity, enough space for 2 things. All right. On the first one, I'm doing arctan. What am I plugging in here first? Arctan of what? 0, right? 0 goes in first. And then arctan of t. Then the other one's going to be arctan of r. Oops. Arctan of r. And then arctan of 0. Any questions at this point? Okay, let's do the things that we know the answer to already. Okay, let's figure out the things that we don't have to take a limit on. And that would be this piece here and this piece here. Arctangent of 0. So hopefully you're not going to go to your calculator for this. The way that I think of arctangent is this. Whenever I need to deal with arctangent, I always think about what the tangent function looks like. So this green function is tangent of x, not arctangent, that's tangent. And that's from pre-cal, and hopefully your pre-cal instructor told you how important this function was. Now, the tangent function is periodic, so it goes, in both directions like this. But when we're dealing with arctangent, we're only focused on the one in the middle, this one right here, the one between negative pi over 2 and pi over 2. So when you say, what is arctangent of 0, this is the output of the tangent function. In other words, the y coordinate. So you're saying where on the tangent function is the y coordinate 0? At what x value is the y coordinate 0? Which is what? I feel lonely today. Everyone's muted.
0.
0, right? So that's right there at 0. That's where the output is 0, right? So I know that that's going to be a 0. I know that that's going to be a 0. Here's the part that's a little tricky. When we take the limit as t goes to negative infinity of arctangent of t, what we're saying is when that is headed to negative infinity, what's the answer, right? So when you look at this tangent, the tangent function, we're saying where is the output of that tangent function negative infinity? So where is that happening?
Pi over 2, approximately.
Pi over 2 is positive. It's going to positive infinity, right?
Oh, negative. That's what I meant. Negative.
So negative infinity.
Approximately.
So you're saying approximately, right? That's very correct, because you are not allowed to plug pi over 2, negative pi over 2 into the tangent function. But this is a limit, everyone. This is a limit. We're saying, what are we getting closer to? What is it getting? What is it approaching, right? So what we can say is that this piece here is headed towards negative pi over 2. That's where it's headed. Now, similarly, where would this one be headed? This limit right here, what have I used? Limit as r goes to positive infinity of arctangent of r. So we're plugging in like positive infinity here. So this one would be what?
Pi over 2.
Pi over 2. In the limit, that's where that's headed. So with all of this said and done, I think I can actually plug an answer in here. We have 0 minus negative pi over 2 plus pi over 2 minus 0. So you wind up getting pi over 2 plus pi over 2. That's 2 pi over 2. You just get pi, don't you? Just get pi. So the area underneath this curve, if you could go forever in both directions, the area is pi. Now remember, pi is just a number, right? 3.1415. So it's a strange answer we got, but it's just the area underneath that curve. That's all it is. Okay, so that is somewhat interesting, I think. It's strange that we got pi as an answer for that. In fact, if you just kind of clear your brain for a second, you're walking down the street, you're talking to some stranger, and you have that conversation. They're like, yeah, y'all are talking about pi and stuff, right? So what is pi? And people will say, oh, well, pi is just the circumference of a circle divided by its diameter. So if you take a circle, if you could calculate its circumference and then you calculate its diameter, then if you take the circumference and divide it by the diameter, that is exactly what pi is. But another definition for pi, if you want, you could define pi to be the integral from negative infinity to infinity of 1 over 1 plus x squared dx. So you could say pi is just as well the area underneath the function 1 over 1 plus x squared on the entire number line. It's just another way to define pi. It's not, I mean, there's nothing fancy about this. There's lots of ways to define pi, but it's kind of interesting that that is a definition of pi if you wanted it to be. So you know how people have, you say, well, how do people actually calculate the value of pi out all these decimal places, right? Like we know pi is 3.1415, right? Like we know that. So how do they do that? Like how can you actually do that calculation? One way you could do it is you could, just go from like negative 100 to 100 on this. And that should give you a pretty decent approximation of what pi is. Shall we try it? Sure, let's do it. Let me go over here. I'm going to ask this thing to do the integral. Let's go from negative t, or I'm going to go negative a to a, and 1 over 1 plus x squared dx. Add my slider. I want it to go out to 1,000. All right, so right now, what it's doing is it's calculating the area between negative 1 and 1. Okay, because I'm going to go from negative a to a, and right now a is 1. So it's giving me an answer 1.57. So as I continue to make a get bigger, it's going to start to slide this out, and you're going to watch this number right here approach 3.14. Oh, it gets there pretty fast. I spoke too soon. All right, so I've gone out to 1,000. I'm at 3.13. That's not very accurate. But let's see. Let's go out as far as it'll go. There we go, 3.1415. See? So the further out you go, the more correct decimals you get for pi. All right. How are y'all doing? Is this, so far, is this better than the techniques of integration, partial fraction decomposition, all that stuff? Let's see what else we want to talk about here. So this is what I just did. If you have an integral that goes from negative infinity to infinity, you want to break it up into two integrals, from negative infinity to a, and then from a to infinity. I like using 0, but you could use any number you want there. And then for each one of these, you have to do limits. Now, in order for this to be convergent, we need both of those to converge. So when you split it into two, to say you have convergence means that both of those limits you do converge, which in our case, it converged, didn't it? So it converged to pi. So let's take a look at these examples. We've done that one. We've done that one. We've done that one. Let's do this one. Negative infinity to infinity, x e to the x dx. And I think what I'm going to do is I'm going to let you get started on this. Let me give you about, I don't know, how about I give you about 5 to 8 minutes to see how far you can get with this on your own. And then what I'll do is I'll just ask for some volunteers, or maybe I'll call on somebody to see like how you approached it and anything you ran into that caused trouble. All right. I'm going to be here. If you have a question, let me know. I'm just going to kind of be on standby. We'll go another 5 minutes. All right, let's talk about this. So first of all, you should have split it up into two integrals. Okay, so negative infinity to 0, 0 to infinity. Go ahead and replace negative infinity with t. Replace infinity here with r. And then you have to find the antiderivative of this. So to do that, you have to recognize integration by parts. And so you go over here, do some scratch work, do your integration by parts, and you get this here in this box. Now what I did one additional step. I factored out an e to the x. Okay, and then this is my expression. So quick poll here. How many of you, yes or no, how many of you got to at least the splitting of the integrals and you got the antiderivative also, and you're kind of at this point here? Okay, good. Most of you got that far. Okay, most of y'all got that far. I don't want to call anyone out here, but whoever didn't, you want to talk about what part you got stuck on? Feel free to not reply, it's okay. Okay, so at this part here, this is where things get weird. We have to split this up. We already have the antiderivative, so we put, you know, all of this here. We're going to plug 0 into this first, so e to the 0, 0 minus 1. Then we plug in t. We do the same thing over here. These two are the ones that are easy to figure out, the ones in the yellow, because we can just evaluate those. E to the 0 is 1, right? E to any, or sorry, anything to the 0 is 1 other than 0 to the 0, but e to the 0 is 1. And so this just gives us -1. And the same thing over here, -1. The problem or the question is this right here. What is the limit as t goes to -infinity of this? And what is the limit as r goes to infinity of this? So I'd like to do those on separate pages. I haven't worked out here, but I want to go through this with you. So we have two limits to address here. The limit as t goes to infinity, -infinity, of e to the t times t minus 1. Then the other one is the limit as r goes to +infinity of e to the r times r minus 1. Let's do the one on the right first, okay? Because it's actually going to turn out to be nice. If we let r go to infinity, e to the infinity is basically going to go to infinity. Everyone agree with that? And then this is infinity minus 1. So times infinity minus 1. Infinity minus 1 is still infinite. So times infinity. And infinity times infinity is infinite. So what we could say here is that that diverges. Now look, in order for this to be convergent, we need both of these to converge. But one of them diverges. So as soon as one of them diverges, the whole thing diverges. All right. So we could be done at this point and just put diverges, but we should go through the limit on the left because everyone needs to remember how to do a limit like this. All right. So t is going to -infinity here. So this is really looking like e to the -infinity times -infinity minus 1. This part is headed towards -infinity times, now where is this headed? This is the part that gets people. E to the -infinity. Where's that going?
Would that just
-infinity.
1 over e to the infinity?
This is going to 1 over e to the +infinity. I'm just using powers, exponent powers to drop the negative, drops it down. And we know that this part right here is headed towards infinity. So that looks like 1 over infinity. Where does 1 over infinity go?
0.
0. So this is headed to 0 times -infinity. And from Cal 1, this is what we called an indeterminate form. There were a bunch of indeterminate forms from Cal 1. Indeterminate forms means forms of a limit that you can't tell me what the answer is. You actually have to do some work. Indeterminate forms are anytime we get 0 over 0, or infinity over infinity, or 0 times infinity, or there's a couple of others. Infinity minus infinity, 0 to the 0, infinity to the 0, 1 to the infinity. Those are all called indeterminate forms. And the way we get through these is using what's called L'Hopital's rule. L'Hopital's rule. So let's do a quick vote again. I think I asked this before, maybe at the beginning of the semester. How many of you remember covering, I'm not saying do you remember L'Hopital's rule, but do you remember that you did cover it in one of your prior classes, Cal 1 probably? Yes or no? Okay, so that's a lot of you do remember that you did that. So what I'm going to do, just in case, I'm going to go to my YouTube channel. Okay. If you go to my YouTube channel, and you go to my Cal 1. Go to my Cal 1 class videos. And where is it here? Right here. This right here. 3337, L'Hopital's rule. Let's see, so somewhere in here I should be doing, yeah, this is where L'Hopital's here. Okay, so there's one place you can find some videos on L'Hopital's rule. Also, if you just go to my playlists, you can find a bunch of old Cal videos too. It's different when you look at it, but you can look up through my old classes and you could watch if you need to go back and review. I've got stuff. And of course there's YouTube just in general. You can probably just type in L'Hopital's rule. Right, and there's thousands of videos on L'Hopital's rule, okay? So if you're having trouble with L'Hopital, just go back and review it, because it usually takes me a day or two to get through all the different types of indeterminate forms. But the key to L'Hopital's rule is this. You must have one of these two forms to be able to use L'Hopital. You have to either have 0 over 0 or infinity over infinity. Right now, we don't have that. We have this case. We have 0 times infinity. So we're still going to use L'Hopital's rule, but what we have to do is we have to make it look like either 0 over 0 or infinity over infinity. Does anybody remember how I can make that look like the form 0 over 0 or infinity over infinity? You remember? You have two things being multiplied. You have to look at these two things, and one of them you get to choose. You rewrite and you drop it to the denominator. So in other words, I'm going to leave the t minus 1 up top, and I'm going to drop the e to the t down. But look, when I drop it, it has to become negative t. Do y'all agree? Now, just real quick, let's let t go to negative infinity. The top goes to negative infinity, but where does the bottom go now? It's not 0. Be careful, because you're plugging in negative here. And it's already got a minus. So this is really going to e to the negative infinity, which is really e to the positive infinity, which is going to infinity. So now you have infinity over infinity, and you can use L'Hopital's rule. Now, what is L'Hopital's rule? What does it say you can do? Once you have it in this form, what can you do now?
Can't you take the derivative of the top and the bottom?
Do derivative of top and bottom separately. So the derivative of the top is just 1. And the derivative of the bottom, be real careful, is negative e to the negative t. I have to do chain rule. The derivative of e to the negative t is itself, but then times the derivative of what's up here, which is negative 1. That's why I have a negative out front. So that's me doing L'Hopital's rule from here to here. So a lot of times you'll see me, I'll circle an L to let everyone know I'm doing L'Hopital's rule. A lot of textbooks will do an H. It doesn't matter, this just lets you know I just used L'Hopital's rule. And now this limit's nice because the top is just going to 1, and where's the bottom headed to? Negative, and then e to the negative infinity. So e to the positive infinity, which is just headed to infinity. And where's that headed? 0. Right? So do you all agree now that this limit here on the left, where was it? This one right here, that limit actually went to 0. So we had this first one went to -1, then we had -0. Everything's great. Over here we had -1. But this one became infinite. And because that one became infinite, the whole thing diverged. So we would say that this is a divergent integral. Questions? You sure?
Scroll down a little bit for just a moment. Sorry.
Scroll down. You want the work I did here or the work on the previous? work
Just the
here?
end of that, where we just were, just up a little bit. Just the bottom of that
Oh,
top.
this
problem.
right here?
Yeah, that's it.
Okay, yeah. So what I've listed here, page 360, page 360, numbers 5 through 22, all of those are type 1 improper integrals. We have not done the type 2, so don't try and do the whole homework assignment out of that section, but those should all be things you can handle. Now, keep in mind, we're in chapter 6, section 6. So when y'all were doing definite integrals, right before this test came, we were doing definite integrals. We actually went back to chapter 5 to do problems. Now we're in chapter 6, section 6. So the book knows, in the book, we've already done all the techniques of integration. So when you do these improper integrals, keep in mind that you might have to do just, basic U sub, you might have a integration by parts, there might be partial fractions, there might be trig sub. Anything could happen in the integral itself. It's just now you have this added element that you have to plug in something, but you have a limit to do also. So we've added a new layer to this. Okay, questions?
I have a question.
Yes.
So I remember in our last exam, we had the homework assignment for 6.6. I was just curious if WebAssigner still had that assignment up, because I think everything closed on the 13th.
It was due already, is that what you're saying?
Yeah, it was due on the last exam because I saw and I tried to attempt it.
You should still be able to get to it.
All of
You
the
can just request to do it late, but don't worry, I'm not going to take off points for you doing it late.
Gotcha. Okay.
Yeah. It was supposed, this material was supposed to be on the second test. We just didn't get to it. Okay, so I'd like to, I don't want to start the second type yet because I don't have quite enough time, but I would like to talk about where this would become useful. Okay, like where would we ever need an improper integral in the real world, right? So this actually has to do with statistics, probability and statistics. So I'm going to start off by first talking about, and I'm not going to test you on this, but I'm also asking you not to just completely tune me out. I'm going to talk first about what's called a discrete random variable. Versus what's called a continuous random variable. Okay, so discrete random variable. So right now, if I asked each of you how old you are, right, everyone would give me a number. And the number you gave me would be an integer, right? Someone would say, oh, I'm 18. Someone else would be, oh, I'm 19. Someone's like, oh, I'm 23. Oh, I'm 31, whatever. And you would have whatever, your list of numbers, whatever they would be, here they are. Those are called discrete random variables because they can only take on discrete values, 18, 23, 31, right? Another example would be how many siblings do you have, right? Oh, I don't have any brothers or sisters. Oh, no, I have 4 brothers and sisters. Oh, I have 1, right? Those are discrete random variables. Anything that you can think of that you could figure out, right, that you could ask someone, or if you were to run an experiment, the data that you look at, right, if the data is integers, then, and there's gaps between the numbers, then that's discrete. That's called a discrete random variable. Another example would be, what if we were to take a 6-sided die and roll it? What are the possible outcomes? Well, we could get a 1, right? One little dot, 2, 3, 4, 5, or 6, right? So this would be a dice. I'll put dice. This is siblings. This is age, right? So every one of those is called discrete. Now, for each of these things, anytime you have a discrete random variable, we can set up what's called a probability distribution. I'm abbreviating because this is not stuff you're going to be tested on. But let's take the die, however you want to say it. Let's create a chart that shows the probability of each of those events happening. So I'm going to do it this way. I'm going to list down here on a number line. Here's 1, here's 2, here's 3, here's 4, here's 5, and here's 6. Now, the y-axis is going to be the probability that number comes out. So if you roll a die, right? If you roll it, what's the probability that you're going to get a 1?
1 out of 6.
1 out of 6, right? 1/6. So here's the way I'm going to do this. I'm going to go half of a unit each way. So I'm going to go to the left 1/2 and to the right 1/2. And I'm going to draw a box. And I'm going to say that box is 1/6 high. Okay. So the probability of getting a 1 is 1/6. How about the probability of getting a 2? Same thing, right?
Also 1/6.
Okay, so I'm gonna draw a box going 1/2 in each direction, and then 3 is the same, 4 is the same, 5 is the same, 6 is the same. Yes? Now, I drew these boxes this way because how wide is each box? Can you tell? I went 1/2 each way. So the width of each box is 1, right? And the height of each box is what? 1/6. So the area of that box is 1/6, 1/6, 1/6, 1/6, 1/6, 1/6, right? That's the area inside there, 1 by 1/6. What would happen if you took the sum of all of the boxes together? So what would the sum of all the probabilities be? What would it be?
1.
1/6 plus 1/6, right? 6 of them, which would be
1.
1. Okay. And that means 1 translates into the real world as 100%. In other words, if I say, hey, what's the probability of rolling a 1? Everyone's going to say 1/6. But if I say, what's the probability of rolling an even number, you're going to do this one, and that one together, right? And that would give you 3/6. That would be 50%. What's the probability of rolling an odd? 50%. What's the probability of every outcome happening? Like, so what's the probability of 1 or 2 or 3 or 4 or 5 or 6? It has to sum to be 100%. That is a foundational piece of statistics, is that the sum of all probabilities has to be 1. Okay? Don't understand that? Let's do another example of discrete random variable. What if I had a box, and inside of this box, I put some, I don't know, let's put some balls in here. I've got 4 red ones, and then I've got 2 greens, and I've got 1 orange ball in there. Okay? Let's try and make a probability. Did I call it a probability density function? Oops. Probability density. It doesn't matter. Density function. Not distribution. That's a mistake. Probability density function. So let's look at a probability density function for this. Okay. So I'm going to pick 1 ball. All right, that's the experiment. I'm going to pick 1 ball. What are the outcomes that could happen? I'm going to pick 1 ball. I could get a red, right? I could get a green, or I could get an orange, right? Those are the 3 outcomes. If I measure 1/2 each way and draw a box, okay, what's the probability of getting a red?
4/7.
4 out of 7, right? There's 4 out of 7. There's 7 balls in there. So this would be 4 out of 7. That's how tall that would be. What's the probability of getting a green?
2 out of 7.
2 out of 7, which would look more like that. And then the orange would be 1 out of 7, right? But if I look at their areas, the area is 4/7. This area would be 2/7. This area would be 1/7. And so if you add up all those areas, you get 1, right? You get 7/7. Again, all probability density functions have that the area is going to give you 1. Now, let's talk about continuous random variables. That's something different. A continuous random variable is a variable that can take on all values, even values in between the numbers. So this would be something like, if I were to ask you how much you weigh exactly, exact weight, let's say. Okay, well, wait a minute, hold on. Of course, you could just step on a scale and say, 180 pounds. But if you have a more accurate scale, you might be able to say 180.1 pounds, right? But if you had a more accurate scale, you might be able to say 180.15. And if it was more accurate, 180.153. And if it was more accurate, you could get more decimals, right? So this depends on the accuracy of your measuring device. But you could have 180.153, but you could also have 180.154. And you could have 180.153296. So there's no gaps. Do you see that? There's no gaps in between. Other examples of continuous random variables would be your height. Okay. Let's say we take a 12-ounce can of soda, right? Do you think that there is exactly 12 ounces in that can? Probably not. Like one can, it might be 11.956. And again, depending on how accurate it is, it could be any value, right? So when it comes to continuous random variables, let's stick with the weight, okay? Let's stick with the weight because I think that'll be a nice one for us to look at. If we look at the probability density function for weight, we're going to have the weight over here. Right, so we're going to measure somebody, okay, and we're going to calculate their weight. Here's going to be the probability. It can take on any value between 0 and what?
Infinity.
Infinity. See, you can't tell me that there's a cap that we put it on. Now, you might not like that idea, but let's do this. Let's put 100 pounds here. What do you think the probability is that somebody weighs 100 pounds? Just if you go out and you take just a human being that's on this planet right now and you just grab them, what's the probability they weigh 100 pounds? More than 0, right? And definitely less than 100%. So I don't know, I'd put maybe a value of that right there. But see, you could also have, 100.1 or 100.2 or 100. So there's all these other things right next to them that you cannot put boxes. You see, I can't go and make boxes anymore. Every single value in between 0 and infinity has to be accounted for. So I think we could agree on this. Do y'all agree that as we go down, when we get to 0, we can actually put a dot? Y'all agree with that? The probability that you take a person that's alive and standing in front of you and you grab them, that they have a weight that's bigger than 0. I mean, the probability is greater than 0, but once you get to 0, then that's not a person anymore, right? So, all right, so I don't know, maybe we go to 200 pounds here. I'm not sure, we're not going to talk about this, but what about 300 pounds? Can you tell me that the probability of someone being 300 is probably lower than 200? Maybe, I don't know. How about, so maybe it looks like this. How about 400? Probability of somebody weighing 400 pounds? It's there, right? How about 500? We're dropping now, aren't we? How about 600? Dropping. Okay, let's go crazy. How about 2,000? What's the probability that somebody will weigh 2,000 pounds?
Like none,
What do you mean like none?
because I
Are you
don't think
saying
anyone
none,
can really
or
live
you
with that
saying
much weight.
You put
I
the
would say
word
a
likely
human
in.
person probably can't.
Pardon?
I would say if we're talking about people straight up, then no. But if we're just talking about living things, then maybe.
Well, I'm talking about like a human being.
Oh yeah, then no.
So yeah, so this is the real question here is, can you say with absolute certainty that a certain weight is not possible? So can you say without absolute certainty that 2,000 pounds is not possible? And you may think, yeah, I can say for sure, no way, 2,000 pounds not possible. But let me give you a scenario. What do you think is more likely? Just listen to this scenario. That someone weighs 2,000 pounds, okay? Or do you think that's more likely, or do you think this is more likely? I'm gonna play lottery tonight and I'm gonna win. What do you think is more likely? 2,000 pound human or me winning the lottery? What do y'all think?
Lottery.
Probably lottery, I would agree with you. I think, but now think of this. What do you think is more probable? 2,000 pound person or me winning the lottery tonight and then on my way home getting struck by lightning and surviving? Still me? Okay, how about me winning the lottery tonight, getting struck by lightning and surviving, and that happening for the next 30 days in a row? You still think me, Ross? Okay, so how about, I mean, so I could keep adding layers to the complexity of what I'm giving you, right? I could say, you know, I get hit by lightning and I get hit by a car, you know, like if it's possible, if it is possible, then you have to assign a probability to it that's greater than 0. It is possible that I could go play lottery and win tonight and get hit by lightning and then go to and do it again tomorrow. It's all possible. So we have to assign some probability greater than 0 to it. Now, it might be that the probability of me getting hit by lightning and playing the lottery 30 days in a row is like 0.000000 with a million zeros and then a 1 at the end. That's like infinitesimal. That's the word we like to use in mathematics. It's infinitesimally small, but it's not 0. So what's happening here, this is the same situation. The probability that a person will weigh 2,000 pounds is so infinitesimally small, but you can't say 0. And so what's happening is that this graph is asymptotically approaching 0. This is what asymptotes are. It's approaching 0. It's never getting there, but it's approaching it. Make sense? So what do we know about all of the probabilities together? If we take the sum of all the probabilities, it needs to add up to be what? 1, right? So whatever this function is, we need to make sure that the integral from 0 to infinity of this function is 1. And that's an improper integral. See, because we're dealing with continuous random variable, everything is possible. All these values are possible. So we have to account for each one of them. And the only way to add up all that stuff together is using the integral. Whereas with the other situation with discrete random variables, you have these boxes that you add up and there's never an infinite amount of them. It's always a finite number. So in probability and statistics, what happens is there's 2 versions of statistics classes you can take. There's statistics that you take that you don't need any calculus. Okay, and you're going to deal with both discrete and you'll deal with continuous random variables. You'll deal with them both. But when it comes to these areas right here, you go reference a table. They give you a table to look at for the areas. So if you've ever seen this, I don't know how many of you have ever taken a statistics course before, but if I put z-score table, you may have seen something like this. Okay, right there. This right here is out of back of a statistics book. And what they do is they tell you, okay, hey, look, if you want to find that area, just tell me what that number is, and then go find that number on this table, and that will give you the area under the curve. But there's no integration involved at all because they know you can't integrate. They don't know, they know that you can't do antiderivatives yet, right? So that's a non-calculus based statistics course. If you take a calculus based statistics course, well, then you can go do the integration and you can get exact answers and you don't have to rely on a table to do it for you. Does that make sense? So the problem that we had earlier, remember this? Integral from negative infinity to infinity of 1/1 plus x squared dx. That answer was pi, wasn't it? So this function right here, oh shit, it's 12:45. I'm so sorry. Y'all can go. That function right there is not an example of a probability distribution function because the total sum of the area is pi. But what I could do, I could just be real clever. I could just put out front, I could just put 1/pi. If I do that, now the answer is 1. And now it is a probability density function. And the most common probability density function that you've ever dealt with in your life is this one right here. It's 1/2 times sigma pi e to the negative x minus mu squared over 2 times sigma squared. That mu is the average and sigma is the standard deviation. This is your standard normal distribution. This is your bell curve. And that is an example of a function that if you were to find the area below that curve, it would be 1. Right? That's the most that's definitely not the most basic. That's the most common probability density function we deal with. Okay, do your homework. Come back on Wednesday. We'll finish up 6-6. We'll do type 2. Sorry, I went over. You'll have a good day. I'll hang out here if you have a question.